Hello, everyone. Thanks a lot for having me. Now, the notion of comprehension is featured in the title, was developed in the 70s in the ordinary categorical framework by Benabou, and later has been streamlined and accordingly been generalized by Johnston in one of the volumes of The Elephant. In this talk, we aim to define this notion in the version of Johnston in Infinity-1 category theory. And we will argue that this is in fact a much more natural, if not the natural environment for it. First, because it intrinsically resolves certain one-categorical shortcomings, both of technical and, say, philosophical nature. And second, because it captures certain intrinsically infinity-categorical structures. Unfortunately, I will not have the time to give the definition of what exactly this notion of comprehension is, because it is rather technical. So instead, let me spend a minute or two on motivating it by drawing back to the original blueprint. Indeed, this notion of comprehension is ultimately rooted in the axiom scheme of restricted comprehension, which emerged in the early days of set theory. Therefore, let's recall that in set theory, we aim to study and formalize naive set theory. A model of a fragment of naive set theory is usually referred to as a set-theoretic universe, denoted by V. And we say that V satisfies the comprehension scheme if for every set X in V in every proper class S, their intersection is again contained in V. This scheme was crucial in the circumvention of Russell's paradox because it gives us a tool to distinguish between small sets and large sets. And it is this distinguishing feature that will carry over to category theory. Following an intuition by Benabou, we obtain the following translation. In our case, we wish to study infinity category theory. And we will do so by picking an index infinity category, V, over some base C, and consider it as an environment for formal infinity category theory, or rather a fragment thereof. Instead of just looking at objects or arrows in V, we will look at arbitrarily shaped diagrams in V. And the role of external structure will be played by shape extensions, where by extension, I mean just an arbitrary functor between infinity categories, which often will be, but does not have to be, a monomorphism. From this data, we can form a presheaf over C, which we can think of containing the J-shaped diagrams, which extend X in a well-behaved way. And then we say that V has comprehension with respect to G if this presheaf is representable for every choice of I diagram X. Thus, the notion of smallness becomes a notion of representability of presheafs. Let's look at the two easiest examples of such comprehension schemes. First, we say that V is small if it has comprehension with respect to the map from the empty infinity category to the terminal infinity category. And if one writes this down, one sees that smallness really is a representability criterion on a presheaf canonically associated to V. And then we say that V is locally small if it has comprehension with respect to the one boundary inclusion. I again will not give the definitions here, but rather just tell you that their interpretation in particularly given index infinity categories over C or associated to C recover very familiar standard structures. For example, depending on the choice of V, smallness of V can express smallness of C in terms of cardinality whenever we are given a Grothendieck universe in which C may or may not be contained. We can express the existence of finite limits in C. We can express contractibility of the core of C. Similarly, local smallness of V can express local smallness of C in terms of cardinality, again, whenever we are given a Grothendieck universe. It can express local Cartesian closeness of C or contractibility of all Hom spaces of C. In fact, these two easy comprehension schemes are exhaustive in the sense that V is both small and locally small, if and only if it has comprehension for every finite monomorphism. Generally, smallness and local smallness are mutually independent, and in fact, in some sense, they're perpendicular to one another. Indeed, we can think of a C-indexed infinity category V to come equipped with two dimensions. First, we have a vertical dimension given by the arrows in the values V of C. And on the other hand, we have a horizontal dimension given by the arrows in the domain category C. In that sense, smallness is a horizontal notion of smallness, and local smallness is a vertical notion of smallness. So what does it mean then to be both small and locally small? Well, whenever C has pullbacks, we have the following very nice characterization, namely V is both small and locally small whenever there is an internal representation of V. That means there's an internal infinity category V in C, which represents V by the way of externalization. Again, I will skip the definition of externalization, but it is fair to think of it as a directed Yoneda embedding. Indeed, the externalization functor from internal infinity categories in C to indexed infinity categories over C is fully faithful, and the theorem shows that its image consists exactly of the small and locally small indexed infinity categories. If we restrict this externalization functor to presheaves, that is C index infinity groupoids, then we recover exactly the Yoneda embedding, and here its image consists exactly to the exactly of the small presheaves, that is exactly of the representable presheaves, representable by an object which is essentially just an internal infinity groupoid. This theorem fails in one category theory, and I think in finite category theory in general, basically because of an intrinsical mismatch between strict and weak structures, which vanishes at infinity. Whenever C is complete, we can characterize those indexed infinity categories which are both small and locally small by exhibiting a left adjoint to them. This is a generalization of the well-known fact that whenever C is complete, that a presheaf over C is representable if and only if it has a left adjoint. Whenever C arises from a model category M, in that model categorical world, we can associate the small and locally small infinity categories over C, being the underlying infinity category of M, to right equivalent functors contravariantly from M to the dual model structure. What I exactly mean here by correspond will be left rather vague. Let me just say that there is a one categorical externalization functor which relates right equivalent functors of this type to homotopical category objects in M. And then in order to relate those homotopical category objects in M to internal infinity categories in C, one has to make a few further assumptions. So let me end this talk with a few examples. The first example is the identity on the infinity category of small infinity categories. This guy turns out to be small and locally small, and as such is represented by the freely walking diagram in the opposite of cut infinity. This is a powerful example because every indexed infinity category over any base arises by precomposition with this guy. And it turns out that comprehension schemes do satisfy transfer principles with respect to precomposition whenever that functor that we precompose with itself exhibits a left adjoint, I think. So we can recover or induce comprehension schemes for many other indexed infinity categories as well. Furthermore, whenever we are given a locally Cartesian closed infinity category C, then we can show that a map P in C is univalent if and only if an associated comprehension infinity category is small. Again, in the world of model categories, if we are given a logical model category in the sense of Arlen-Kapulkin, then there is a syntactic notion of univalence and other important related notions, and those can be characterized again by right equivalent conditions of respective one categorical externalizations. Due to the last example, we can characterize elementary higher toposes and Grothendieck infinity toposes in terms of comprehension schemes. Namely, they are characterized by well-poweredness, which is a generalized comprehension scheme, together with the existence of a cover of small neighborhoods. I will not exactly explain what this means, but it is quite interesting that they appear to have a manifold-like quality in this sense. And lastly, it also turns out that the externalization construction of internal infinity categories does arise a lot in the literature in a dual sense, namely in the form of nerve constructions of internal infinity co-categories. So in conclusion, the point I wanted to make is that infinity one category theory is in fact a natural habitat for this rather classic by now notion of comprehension schemes. Furthermore, that this notion of comprehension is not a fringe notion, but it does express a lot of structures and properties which are very relevant to all sorts of category theory. And lastly, that if we look at this notion model categorically, that it can be expressed in terms of right equivalent conditions, and that it does cover notions which are relevant to the semantics of homotopy type theory and homotopical algebra in general. Thanks a lot for your attention. That's it from me. Goodbye.